applications of integrals to kinematics. So we've already know that if you take the derivative of displacement, you get velocity. And if you take the derivative of velocity, you get acceleration. So displacement with S, velocity with V. This way is the derivative. But if we wanted to work backwards, we would have to integrate. So now we can have integration also help us with kinematics questions as well. Okay, and we got some good questions coming up. So how do these questions start? Well, they could tell you something like, the acceleration of a particle is given by that formula. Can you find the equation for velocity and the displacement given that s equals 0 and v equals 8 when time equals 0? So what they're giving us here is time is 0. This would be the initial velocity and the initial displacement. So if I have my acceleration formula, then my velocity formula will be the integral of acceleration, which is t plus 1 dt. Simple integral to do, but then you would have a plus c here. So we get a velocity formula, and what do we know? We know the initial velocity is 8 when time is 0. So if I plug in 0 for t, I can solve that c would have to be 8. And so I know my actual velocity equation is t squared over 2 plus t plus 8. My displacement formula then would be the integral of that. And since we already used the letter c for velocity, this time when we add our constant, we'd have to go plus d. If you plug in, since the displacement is 0 at time 0, we can solve by putting in 0 for t and 0 for s and find out that d would also be 0. So our final equation for our displacement would just be that. So I'd like you to try the next two. So we've got our velocity. If we want to go from velocity, again, I often write out off to the side to remind me which is going in which direction. I want to go velocity to acceleration, so I'm going to take the derivative, and the derivative would be negative 10 meters per second squared. Initial displacement is 40 meters. That means when time is 0, s is 40. And now we're integrating backwards from velocity to integration. We have to plug in 0 for t and 40 for c, 40 for s to figure out that c is 40.
Can we just skip the final c?
Because you know it's 40. In this case, if you just wrote it down, it'd be fine because it is quite simple. But when you integrate this, it should have a plus c. But if you want to just write the answer right after that, if you can do that in your head, that's fine. Okay. Again, off to the side. So, So we're given the acceleration, we're given that at time 0 we have an initial velocity and initial displacement. We want to find the velocity, so we integrate. Again, find out that c is 3. For the displacement, we can integrate our velocity. Since we use c in part A, I'm going to use d here in part B. And the initial displacement was 2, so we can figure out that d is equal to 2. Good. The values when the particle is at rest. So this is some language in the question that's supposed to tell you something. In a moving object, if it's at rest, it's not moving. How does that show up in these equations that we have? The velocity would have to be 0. So this is telling us our velocity is 0. Then we have to make sure that we go to the correct equation, which is our velocity equation, set it equal to 0. This one you could factor. Make sure you include your units, since it is a word problem. We had seconds in the question to begin with. So when we write our answer, we include our units here at 1 second and at 3 seconds. And then if we want to find the displacement at these times, we'd have to plug in 1 and 3 into our displacement formula. And again, use our units here since it was in meters per second. We would have at 3.33 meters and at 2 meters. Squiggly for approximation? Not so much. But you should still. If you this technically, since I rounded, should have approximation signs instead of equal signs. It's good practice. I'm not going to dock you marks for that. Okay, so the next idea that we're going to look at is a difference between displacement and distance. So if I take a ball, do I have, no, I don't have 2 meters in this classroom. I'll hit the roof. But if I throw it up a meter and catch it at the same place, we would say that the displacement is 0. Started in my hand, it ended in my hand. It's exactly the same place, right? If you're watching this video at home, you don't even know if I threw it up in the air. But if we throw it up 1 meter and it comes back down 1 meter and someone said how far or what distance has the ball traveled, well then it would have traveled 2 meters. And on the smartboard I have a 2 meter example, but then I would have hit the roof. I guess I could probably get really low to demonstrate. I don't know, was that 2 meters?
No, because you catched it higher than 3.
I'm so nervous about it. Okay. Did you ever in grade 11 do this problem? How far does that ball travel before it stops?
Yeah, it's a series question. Geometry series.
Yes, because it always bounces up a certain percentage of what it fell. You can add them all up as an infinite sequence. But we're not doing that right now. What happens then is, according to integration, right? Displacement is the integral of velocity. But if you take the integral of velocity, you'll get displacement. So when I throw it up in the air and catch it, that won't be my distance. Because when it's going up, it's a positive displacement. When it's coming down, it's a negative displacement. And it cancels out. But if we break up our integral according to what parts were below and what parts are above, and we take the absolute value of those parts that are below, that will change that negative displacement into a positive distance, and then we can calculate the total distance involved. All right. Last two questions we're going to look at. How many of you have taken physics or are in physics? Excellent, almost everybody. So, you probably have physics formulas that you are used to for the following questions. But we're going to say, we've forgotten all our formulas. Could we use calculus to figure out the same things? Here's our first question. Okay, a golf ball is thrown upward with a velocity of 7 meters per second from the edge of a cliff 75 meters tall. How long will it take the golf ball to hit the ground at the bottom of the cliff? This is on Earth, so we will assume regular gravity. Okay? So a good start is to draw out a picture. You've got a cliff 75 meters tall. You've got a golf ball thrown off the cliff in an upward direction. What's going to happen to that golf ball? Gravity is going to make it come down. It's going to hit the sand down here. Well, vertically upwards or whatever angle, if the vertical doesn't matter. Okay, you could throw it straight up, or I could throw it forward with that vertical initial velocity of 7 meters per second. Right. Okay? So this is the idea of what's happening. And it's going to hit the ground right here. How do we use calculus to figure this out? Well, we start by writing everything that we know. Okay, off to the side, sva. Okay, we know acceleration due to gravity, negative 9.8 meters per second squared. We know that when time is 0, the initial velocity is 7. And we know when time is 0, the initial displacement, if we consider the ground at 0, we're 75 meters above the ground. What are we trying to solve for? We want to find the time when it hits the ground, and if we use 75 as our initial cliff, then the time would be when s is equal to 0. We've set this all up because now what do we have? We have all the information to work back and integrate as we go along. So first of all, if I want to find my velocity formula, I could integrate negative 9.8 meters per second with respect to time. That would give my velocity formula to be negative 9.8 t plus c. And since my initial velocity is 7, I know that c is equal to 7. if I want to find my displacement formula, I can integrate this. And since my initial displacement is 75 meters, I can solve for d to be 75. Just change this to negative 4.9 t squared plus 7t plus 7.5. What are we trying to find? We're trying to find t when s is 0. So now we could substitute 0 in. And solve for t. Obviously, real-life problems don't factor nicely. Usually, they don't work out to be nicely factored. So then if you can't factor it, either you'd have to use a program on your graphing calculator or the quadratic formula. Quadratic formula, negative b plus or minus b squared minus 4 times a times c, all divided by, oh, there's a negative. Good. All divided by 2a. Got a little nervous there. I didn't have a negative and there was going to be no solutions. So go to my calculator now. Type this in. Those approximation signs. I'm going to round it to two decimal places. Negative 3.26, or t is .69. Are we done?
No.
No, why not?
Negative.
Yeah, this answer we would have to put an X through. You can't throw it up in the air and then say, yeah, it landed 4 seconds ago before I threw it. Or 3 seconds before I threw it. Why does that happen? Well, our equation makes a parabola, right? So if we had drawn that part of the parabola, this would be the negative 3 point, was it 69? 29? 26. 3.26. This is going to be the 4.69. That's where the 69, okay, perfect. That's 4.69, and that's the one that's going to make sense. What are we dealing with our units? We were in meters per second squared. So we have to make sure that we include 4.69 seconds here. Fascinating. No formulas needed. We needed to know what gravity was. We needed to know how to integrate. But we could solve this otherwise. Yes?
If you get the exact same formulas,
Like when we integrate, you get the same formulas? So what are your physics formulas? Because I don't have any physics formulas memorized. Equals 1/2 at squared plus ut. And u is initial velocity. So it's the same idea. We just work backwards to get it. Okay? Level 1 question. Not too bad. So again, what did we do to sort of help us set this up? we drew a picture, okay? Drawing the picture is nice because especially if you feel like you don't know how to do a question at all, at least it makes you feel like you're doing something important. Okay? Then I wrote out everything that I knew to see if that would somehow help me figure it out. And then in this case, the integration worked out perfectly, and we were able to solve it. Second question, a little bit harder. Nathan designed a car that would increase its speed steadily until it reached 100 kilometers per hour. Perhaps this was some kind of thought that if you maintain a constant acceleration, your gas mileage will be better, and so if you could just get onto the highway and push a button, your car would just perfectly increase until it reached the speed it wanted. Maybe you would get better miles per gallon or liters per kilometer, depending, okay? Liters per 100 kilometers, right? That's how it's the metric system and the imperial system are really different in figuring out efficiency of your car. Okay? One day he set out on the highway, just sat his car down there, pulled it out of the garage and dropped it right on the highway, and reached his cruising speed 20 seconds later. How far in meters did he travel in those 20 seconds? So again, we try to write out what we know. Okay, we know at time equals 0, the initial velocity is 0, the initial displacement is 0. Those are the things we know at time equals 0. At time equals 20 seconds, the velocity will be 100 kilometers per hour. And we want to find out what S is at that time. Off to the side, just to remind us of everything that's in order. Now, a couple of things to notice in this question before we even get started. What's going to be problematic with the numbers that I wrote down? They're in different units. Okay? Time is in seconds, velocity in kilometers per hour. How far in meters did he travel? So if we want our answer in meters and we have our times in seconds, we're going to need to change this velocity from 100 kilometers per hour into meters per second. How do we do that? Divide by 3.6. Okay, that's doing a lot of, you've obviously done this before, because that would not be the natural thing that just comes to my head, oh, 3.6, right? But if you wanted to do it the longer way, right, you would have to say, well, hours, there's 60 minutes in an hour and 60 seconds in a minute. So that becomes 3,600, right, on the bottom. And you would have kilometers to meters. There's 1,000 kilometers in a meter. So you'd have 1,000 on top and 3,600 on the bottom. Sure enough, that simplifies to divide by 3.6. If we do that, that's not a very nice fraction. Okay, a couple of things with your calculator that you could do. I like some of the fancy stuff in your calculator. 100 divided by 3.6. That's a negative sign. 3.6 is 27.78. Math fraction happens to be 250 over 9. I'll write it as 27.8 meters per second or 250 over 9 meters per second or 27 and 8/9. No, 27 and 7/9. Apologies. Okay. So now our units are all the same. What does it mean in that first sentence when it says designed a car that would increase its speed steadily? The acceleration is constant. Okay? So this is what I know. The acceleration is something, but I don't know what it is, but it stays the same. It doesn't change. What letter would you like to use? Constant starts with a K. Should we go like that? I mean, constant maybe in German starts with a K. So we could go that our acceleration is some number, but we don't know what that number is. It doesn't seem like we have enough information right now, but we could work backwards and say, well, my velocity is going to be my integral with respect to time. And so my velocity is going to be kt plus c. And since I know my initial velocity is 0, I know that c would equal 0. So my velocity is just kt. Looking back at the information that I said I knew at the beginning, I have at time 0 velocity 0, but I also have at 20 seconds the velocity was 250 over 9. How is that helpful? I know that when t is 20, I don't need that extra 0. When t is 20, the velocity is 250 over 9. Which means I could plug in 250 over 9 for v and $20 for t, divide both sides by 20. Are you okay when I do this all at once, mental math-wise, when I divide it by 20? How did I get that? Dividing by 20, the zeros would cancel out. And then having that extra 2 on the bottom would make it 18. So now we know our acceleration is 25 over 18. What are our units? Meters per second squared.
This be a calculator or non-calculator question?
That dividing by 3.6 is kind of calculator-ish. So I would guess that this would be calculator.
So you would go to calculator.
And now we can find our displacement by doing the integral of our velocity, and our velocity equation is now 25 over 18t . And again, since our initial displacement is 0, we know that d is equal to 0. So our displacement formula is 25t squared over 36. How far did it travel in 20 seconds? Well, this should be some good mental math. Okay. Do we know how to do some easier simplification here if I want to write this in lowest terms. A couple of things that we can see here. I'm going to just go, for mental math, this is good. 20 is 4 times 5 times 4 times 5. 36 happens to be 4 times 9. So I know that these 4s would simplify. I know in the 25 is 5 times 5 that there's no common factors in 9 and what's on top, because 9 is just 3 times 3. And so what I have in the end is 5 times 5 times 5 times 5 times 4, which I might, if I was doing all over 9, if I was doing this mental math, I would probably do that. 5 cubed is 125 times 20. (2,500 over 9 meters). Roughly. Wow, that 7 got really bad. 277.8 meters in 20 seconds. That's interesting. I'm just analyzing the answer a little bit, right? What's the world record for the 100 meters? About 10 seconds, right? So then, and I think the world record for the 200 meters is around 20 seconds, just under. They're just under for both. I think that, I'd have to check this. But in my head, the 200 meter cut in half is faster than the 100 meter because you've already reached your fast speed and you're able to maintain it. So when we think about those athletes starting from 0 and accelerating to get to finish in 20 seconds, 200 meters, this vehicle got up to 100 kilometers per hour in 300 meters in that amount of time. I don't think I could beat a car going 100 kilometers an hour in any race. But it's not that much of a difference.